Eva. Thank the organizers, first of all, for the invitation to this beautiful place, nice conference. It's been quite a pleasure to learn about what's going on in the Munich area and lots of nice discussions. So I guess we're switching gears a little bit to metrology and sensing. And as such, I hope I can convince you in this talk, if you maybe don't already know, that defects in diamond are quite an exciting platform for metrology, in particular as applied to, say, condensed matter systems in my lab, and I think also to biological systems, which I won't talk about much here. Before I start, first want to acknowledge the team, in part to make sure I don't forget at the end of the talk, but also in part, I think I want to acknowledge the collaborators that we have as a testament to the sort of, I think, versatility of the NV Center as a sensor as to the various fields that it can touch. We collaborate with Andrea Young on imaging graphene, Andy Lucas, a theorist who helps understand hydrodynamics in graphene, also applying NV centers in sort of many body interacting quantum systems as applies to metrology and also quantum simulation broadly, and a theory. This is with collaboration with Nora Miao, who I guess was here yesterday, and then also a material scientist, Kunal Mukherjee at Stanford, with whom we collaborate on the synthesis of diamond, which I'll talk about a bit as well. Many of us, I think, are familiar with the NV Center and diamond, so I'll just give the one slide introduction to what these defects are. Here's a schematic of the carbon lattice. If one replaces one of the carbon atoms with a nitrogen and the nearby carbon atom is displaced, forming a vacancy, one can get this NV complex. And in some ways, this exhibits sort of a nice marriage of atomic and solid-state physics. We have a solid-state host that's housing these atomic-like systems. These atomic-like defects, I call them atomic-like because they feature an optical transition. They feature an electronic spin, an effective two-level system. In this case, there's a spin triplet consisting of 3 states in the ground state, but really we can choose any of these 2 states to form our canonical qubit. This qubit is very long lifetime, surprisingly long at room temperature for a solid-state system, on the order of millisecond quantum coherence times. And this optical transition allows us both for optical pumping and preparation of the qubit and also of readout. Now, importantly for the field of sensing and metrology, this 2-level system here is sensitive to a variety of fields. It's sensitive to magnetic fields, to strain fields, to temperature, to electric fields. And because the sensor itself is so small, we can sense and image these fields with very high spatial resolution. I'll mostly be talking about magnetic field sensing. This is one of the most developed sensing applications of the NV Center. And so very briefly, how does magnetic sensing with this NV Center 2-level system look like? So if I zoom in here on the ground state spin triplet qubit levels of the NV Center, the 0 and the plus and minus 1 state, in the absence of any magnetic field, these, the 0 and the plus and minus 1 states are split by what's called the crystal field, or zero field splitting. And that's in a nice convenient frequency range of 3 gigahertz, which is commercially easily available. And I mentioned that there's optical transitions, and there's optically detected spin readout, meaning optically dependent spin readout, meaning that if the spin is in the 0 state, it emits more photons than if the spin is in one of these plus and minus 1 states. So this allows for a technique called optically detected magnetic resonance. A plot shown here shows as we simultaneously irradiate the NV Center with light and sweep the microwaves that we're driving the NV Center with, we see a dip in the fluorescence of the NV Center when the microwaves are resonant with this transition. In this way, we can spectroscopically identify exactly what the splitting is in a very quantitative fashion. Now, in the presence of a magnetic field, of course, as you know, through the Zeeman effect, these plus and minus 1 states will shift, again, in a very quantitative way, by an amount given by just gamma times b, which is about 5.6 megahertz per Gauss for this electronic G equals 2 system. And hence, taking an optically detected magnetic resonance sweep, one can now see 2 dips in this resonance spectrum corresponding to the transitions between the 0 and the minus 1 and the 0 and the plus 1. And so the distance between these is exactly related to the magnetic field in a very quantitative fashion. So thinking about the sensitivity of such a sensor. The sensitivity can be parameterized by a few parameters, really the susceptibility gamma, a parameter C that corresponds to the fluorescence rate as well as the optical contrast between, say, the 0 and the 1 states, and also the T2 time. So the wish list that we'd like to have long coherence, long T2. The longer the T2, effectively the narrower these lines become and the easier it becomes to resolve shifts and hence magnetic fields. And of course, having higher photon counts will give us a larger signal, and having a larger optical spin state contrast will increase the difference, fluorescence difference between these two states. So those are, that's basically how the NV center works as a sensor. So in particular, I think one exciting application of NV-based sensors is in local nanoscale spatial imaging of various samples, in particular condensed matter samples, where it's possible now to integrate single NV sensors at the apex of a scanning probe tip, scan it over some sample of interest. And there's some exciting features that this platform has. One is the high sensitivity. So an NV sensor can reach about nanotesla per square root of Hertz magnetic field sensitivity. Just to put that in perspective of some known numbers, a single electron spin, if I have a single electron spin, if I'm 150 nanometers away from that spin, that corresponds to about a nanotesla. So we can sense single electron spins. Single nuclear spins, if we're 15 nanometers from a single nuclear spin, again, that produces about a nanotesla field. I will say that this is achievable in the bulk. There's some challenges that I'll talk about later in terms of achieving these types of sensitivities near the surface. But this is, I think, not infeasible in such a geometry. Of course, the atomic scale size features means that we can get very high spatial resolution in these types of imaging experiments. NV sensors are very easy to use. Tabletop experiments, simple confocal microscopes, commercial microwaves available, commercial light sources available, and importantly, the NV sensor works over a large range of temperatures from low temperature up to 400 Kelvin and even higher, allowing us to, for instance, probe phase transitions in condensed matter systems. It's quantitative, I already mentioned that, but I think that's an important feature that differentiates the NV sensor as a magnetic sensor from other magnetic sensing platforms such as, say, MOC or MFM. And also, it's compatible with many target systems, being non-invasive, robust to a variety of environments. One can sense things at the surface or below the surface, which, for instance, STM cannot do. There's been lots of advances in scanning probe microscopy with NV sensor spins. Here just shows some nice work from the Jacobi group a while ago, where they used an NV sensor to sense actually an image, another NV sensor, but a single electron spin. And the group of Patrick Malatinsky in Switzerland, they've been scanning NV sensor magnetometry to probe 2D magnets. And again, in Amir Jacobi's group, using NV sensors to image magnon scattering. In our group, we have had, there's just a sampling of some of the experiments that we've performed where we can image current flow and monolayer graphene. In fact, I'll talk about this a bit more today, but some other previous experiments have included imaging vortices in superconductors and imaging the texture of magnetic skyrmions in sort of magnetic multi-layer devices. So again, I hope as a background, can show you that the NV sensor is already being useful in imaging and condensed matter systems and quite applicable to a variety of them. This is a brief outline. I'll tell you a bit more about our NV-based imaging of electron flow and monolayer graphene. And then I'll move at the end to kind of give a quick highlight of some of the challenges and opportunities that I see with NV sensor sensing. One of the challenges will be the surface-induced decoherence. When you bring an NV sensor near a surface, surfaces are notoriously messy, and that causes some undesirable effects, but we've come up with some ways to mitigate that. I think there's some new opportunities in terms of novel imaging modalities. I talked to you about the sort of basic method of sensing, just looking at shifts in an ESR peak, but there's some exciting imaging modalities in terms of looking at noise. And I think another exciting direction is, instead of using a single NV sensor, leveraging multiple sensors and leveraging potentially entanglement between those sensors. Okay, so This just shows you the platform I think the workhorse of our scanning probe system. So we make diamond cantilevers that have a single little nanopillar at the end, and we engineer there to be a single NV center at the very apex of this probe, residing about 20 nanometers below the surface, so we can bring it quite close to the system under study and get good spatial resolution. And if we take a confocal image of one of these cantilevers, you can see here as we scan the laser, we see enhanced fluorescence coming from the NV center. Just to give you a sense of the scale, getting about 100,000 photons per second from such a NV center. Okay, so as I mentioned, I'm going to tell you about imaging electron flow in monolayer graphene. Okay, why? Well, when you think about electrons moving through a electronic or condensed matter system, there's a variety of different ways that electrons can move through a material. Typically, for condensed matter systems, we're familiar with two regimes of transport, diffusive and ballistic, right? So in the diffusive regime, which is typically observed at room temperature and in also sort of dirty materials, electrons moving through the device will scatter off of impurities or off of phonons before they have a chance to scatter off of the walls of the device or off of each other. And these phonon and impurity scattering can be characterized by LMR, which is the momentum relaxing lengths, because they relax the momentum of the electronic system. In this case, LMR is smaller than the width of the system or any momentum conserving scattering events, such as electron-electron scattering. In the ballistic regime, which is typically seen in very clean materials, such as graphene or gallium arsenide 2-degs, at low temperature, electrons whiz through the device and scatter off the boundaries, usually of the system, before scattering off of anything else, kind of acting like billiard balls. And in this case, this regime is characterized by the size of the device being smaller than either of these momentum relaxing or momentum conserving scattering events. And in this sort of, I'd say, rather unusual regime for condensed matter systems, but of course very common for real fluids, such as water, electrons can scatter if the electron-electron scattering is strong compared to the momentum relaxing length or the size of the device. One can reach this hydrodynamic regime where electrons can begin to be described by these sort of bulk parameters such as viscosity and density and behave like fluids. And this is, I think, an interesting regime that has attracted some interest of late. There's been some transport experiments which have revealed signatures of hydrodynamics. These are just a few over the past several years. And by looking at effectively the resistance, 2-point measurements as a function of temperature or carrier density, revealed features that are consistent with hydrodynamics. But oftentimes, the results are interpreted with these spatial images of what the current flow would look like in this regime, right? But so we were motivated to actually directly image these the systems and reveal hydrodynamic effects in a direct way. So together with Andrea Young at UCSB, who fabricated monolayer graphene devices, and in these devices they formed a slit. And the reason that we formed a slit in these devices is because the spatial distribution of electronic transport through the slit will have signatures that are characteristic of these different flow regimes. So in the ohmic regime, if you plot here, what's plotted in the color scale is the current density flowing through the device. You can see that the current density is kind of peaked near the edges of the slit. Here's a 1D line cut taken across the slit that shows that the current density has these sharp ears. We call these ohmic ears at the edges of the slit. And one can think of this a little bit as a lightning rod effect. Then in the ballistic regime, as expected, the current flow across the slit should be constant. The electrons really don't see the slit. They just whiz by depending where they start. They don't feel the edges of the slit. In the hydrodynamic regime, one expects to see a bit of a rounding of the current flow profile in the slit. And just as a reminder, I think I didn't say this earlier, and maybe it's obvious, but I've talked about magnetic sensors here. I'm talking about imaging electron flow. And of course, the relation there is that as we know, moving electrons produce magnetic fields. So through the Biot-Savart law, a moving electron, we can sense the field that it produces and back out the spatial patterns of the electron flow in the device. And of course, we should be able to move around in the parameter space of ohmic, ballistic, and hydrodynamic flow by varying the momentum relaxing and the electron-electron scattering lengths, which can be varied with density and with temperature. So here are the first results at room temperature. On the left, we imaged the magnetic field and then deconvolve the images to extract the current density. By the way, this is a one-to-one mapping. One can get the current density in this 2D device from an image of the magnetic field in a plane above the graphene structure. And so this looks very much like the ohmic predictions that I showed on the previous slide. And indeed, this isn't even a fit, really. It's a free parameter, no free parameter prediction for the data that shows at room temperature. In this case, we're at the charge neutrality point. We see flow consistent with ohmic flow. This is, again, a simulation. This is sharper because this is a simulation of the current in the device. This is our estimated current. But again, our NV center resides about 50 to 100 nanometers above the surface of the graphene, and hence there's some rounding of these structures. Now we expect that as we go to lower temperature, and phonons the electron phonon scattering is reduced, we should approach this hydrodynamic regime. And so here shows several images taken at two different temperatures, room temperature, 128 Kelvin, at varying electron density. And here shows the line cuts, just for easier visualization, across each slit. And the point is here that at room temperature, again, we have these ohmic ears at all charge densities. And as we go to this lower temperature, where we kind of expect hydrodynamics to emerge, at charge neutrality, we still see the ohmic ears. That's kind of expected because at charge neutrality, there's both electrons and holes, and there's a lot of enhanced electron-hole scattering, which contributes to momentum-relaxing scattering, and hence ohmic behavior. But as we increase the charge density, we see a distinct transition to non-ohmic behavior. Okay. The question is this ballistic or hydrodynamic? For that, we had to take a really closer look and look at the statistics and the errors. Here just show some error plots of comparing the images to predicted images in the ballistic, or as a function, so the predicted images as a function of the momentum relaxing electron-electron scattering length, and seeing where the smallest residual error is. These red dots show the closest fit of our data to the simulation, which is consistent, again here, the LMR being on the order of several microns, and the electron-electron scattering length being on the order of submicrons, show indeed that this is consistent with collision-dominated transport. I should note that this is consistent with some results from the Alani group in Israel, who used a different technique, showing sort of the ballistic to hydrodynamic crossover. Also, interestingly, a bit at odds with some of the work done in the Jacobi group, showing that showed non-ohmic behavior even up to room temperature. However, we think we understand this discrepancy. But of course, I'd maybe say it's one outstanding question. This resolution between the ballistic and the hydrodynamic regime is not extremely sharp in terms of the amount of rounding. And as one future direction, we are thinking about other geometries that could more conclusively and directly, more obviously without a lot of data analysis, determine this, resolve the difference between ballistic and hydrodynamic flow. Here I show on the right, actually a speaker later today from Eli Zeldov's group, I don't know if he'll talk about this, but has demonstrated some other nice geometries which could be good at resolving ballistic and hydrodynamic flow. And some other future directions that we're currently working on now are looking at bilayer graphene, exploring magnetic features in the phase diagram of bilayer graphene, and looking how the current flow is, what the current flow is in those regimes, and looking at anisotropic transport in bilayer graphene, which has an anisotropic Fermi surface, and hence should be a nice way to distinguish ballistic and hydrodynamic flow. Okay, so I'm running a bit low on time, so I will just try to give you a flavor of some of these challenges and opportunities that I mentioned that I see moving forward for NV-based sensors. So, as I mentioned, to have very high spatial resolution and better sensitivity, you want to bring your sensor as close as possible to the system under study, but that comes with being sensitive to uncontrolled features on the surface. We in the past have shown that the NV's coherence time degrades as you bring the NV center close to the surface. Okay, and this is something that has to be battled. I already mentioned some of these other opportunities that I'll briefly talk about. Let me first talk about this surface-induced decoherence and one of the ways that we've recently demonstrated to deal with this issue. So it turns out that shallow NV centers near a surface, there's some surface spins that exist on the surface. We actually don't really know what these are coming from microscopically, but we know that they exist. We can spectroscopically resolve them through double electron-electron resonances. We can even drive Rabi oscillations of these surface spins on the surface, which I find pretty amazing, right? There's these spins, we don't even know what they are. They're sitting there at room temperature and ambient conditions, and yet they have actually a pretty reasonable coherence time. You can see Rabi oscillations. In any case, they exist. They contribute to decoherence. So one perhaps counterintuitive way to deal with their decohering effect is just to drive them harder. This is an analogy to motional narrowing in magnetic resonance, where if I have an environment that's fluctuating, if I drive it so fast that it fluctuates really quickly on the time scale of, say, the coupling of my spin to its environment, I can effectively average their effects to zero. And so we did this. We drove these spins very fast. We showed that we can extend the coherence of the NV center by driving the environment effectively. And we've now shown two different ways of driving. We can drive with a monochromatic drive. We can drive with a polychromatic drive. I think there's also some interesting future directions. If you have some environment that's fluctuating and you can identify its spectroscopic features, you can drive it with sort of catered drives to optimally decouple your defect from the environment, or your qubit from the environment. It's also, I think, kind of nice because we're not touching the qubit at all. We're not touching the NV center at all. All we're doing is dealing with the environment. So that leaves the NV center totally free to do whatever gate operation or whatever sensing operation you'd like. So under the drive, we can show that we can also extend the sensitivity by up to a factor of 5 for these very near surface sensing ready NV centers. I think just going forward, there still is lots of questions about the origin of the spin and also charge instabilities at the surface. NV centers near the surface also begin to become a little charge unstable. I should say things are not that bad. They're still very useful near the surface. In fact, Dominic Bucher locally here at TUM has done some really nice work using shallow NV centers for more sort of wet and squishy biological imaging things. But I think understanding these surface-induced decoherence will really help these experiments move even further. And so I think this is one direction going forward. Now let me talk about, so I've told you mostly how we use just DC sensing, or effectively one can also use AC sensing for coherent sensing, but the NV center is also sensitive to magnetic noise. Briefly, if I have a qubit, a two-level system, and it's subject to noise, that has a frequency component matched to that two-level splitting, I'll get a reduction in the relaxation time, in the T1 time. Okay. And because I can tune this energy splitting, I can actually do spectroscopic investigation of the noise environment. And also, I can move my NV center different distances from my sample under study, and thus also produce a filter function in momentum space, in K space. If I'm at some distance d, my NV center is sensitive to fluctuations at a momentum 1 over d, effectively, or 2 pi over d. So I think these are some nice theory papers, largely from Eugene Demler, who have predicted how using noise spectroscopy with an NV can reveal different transport regimes, in this case, ballistic, hydrodynamic, and diffusive. Also looking, using noise magnetometry to diagnose magnetic ground states of exotic magnets, and for instance, reveal spin liquid ground states. I'll just show you that as a start, we have done this type of relaxation imaging where we brought an NV center close to, in this case, a conductor. A conductor has Brownian motion, thermal fluctuations. The electrons are moving around randomly and hence produce magnetic noise. And we can measure that magnetic noise using the relaxation time of the NV center. It's shown here. This is omega, inverse of the relaxation time at 1 over T1, is proportional to the magnetic noise spectrum, which depends on my distance from my NV center to my sample temperature and the conductivity. And so really what we were able to do is image the conductivity of a patterned silver film. And here I'm just plotting T1 of the NV as a function of position, and see that the T1 of the NV is locally changed when we bring our NV center near to a conductor. So this is sort of a first step towards some of these more, realizing some of these nice proposals from Eugene Demler. And then lastly, in the last 2 or 3 minutes, I want to talk about possibility of leveraging multiple sensors. So we're motivated to engineer 2D dense ensembles of spins. One, because if I have a 2D, first of all, if I have a dense ensemble, I can improve my sensitivity by classically square root of the number of spins. If they're entangled, by n, the number of spins. And also, if they're in 2D, that offers 2 possibilities. One is I can have higher spatial resolution because they're limited to 2D. It also turns out that if you want to use dipole-dipole interactions as a method to produce a particularly relevant entangled state, a spin squeeze state, one can do this with spin-spin interactions, but you have to be in 2D. In 3D, these spin-spin interactions will average to 0 and not lead to any spin squeezing. It turns out that for 1, 0, 0 diamond, actually, the dipolar interactions, even in a 2D layer of spins oriented this way, averages to 0. It's very unlucky, but that's the exact angle over which dipolar interactions average to 0. So if you can make NV center spins that all point up in a 2D layer, that would be really exciting. That's something that we've actually recently done, so I'll show you that. We do this with diamond growth. We have our in-house CVD growth chamber. We're able to grow diamond, very thin layers of diamond, introduce nitrogen in a very thin delta-doped layer, and then continue to grow a diamond on top of that. We can introduce nitrogen. We can introduce the vacancies via local low-energy electron radiation. It turns out that our delta doping technique is, I think, quite superior to the standard method of implantation where people generate NV centers by implanting nitrogen. Here are 2 profiles, SIMS profile, secondary animass spectroscopy, that measure the nitrogen concentration as a function of depth in the material. So here's our grown layer, and we see we can confine our nitrogen to a nice 3 nanometer thick layer, probably limited by the resolution of the SIMS, actually. When you try to do the same thing for implanted nitrogen, you see a much broader distribution because of channeling, So we've taken these 2D layers. First of all, we saw in SIMS that they're 2D. We also, in a collaboration with Norm Yao, used the NV centers inside of this bath of nitrogen spins. And using the decoherence dynamics of this interacting spin bath, we were able to extract the dimensionality of the bath because the decoherence profile should have an exponent. So if you have a stretched exponent of your decoherence profile, that stretched exponent, depending on if you're in the sort of short time or long time regime, should reveal the dimensionality of the bath. Here, D is the dimensionality, alpha is the power law of the interactions. So if I have a strongly interacting system, dipolar interacting system, alpha equals 3, and then depending on the dimensionality, I should have exponents that reveal that. And so, in short, we did this with our 2D samples, our 3D samples. The exponents agree with what we expect. We've now started growing on the 1, 1, 1 direction and see that we can get this aligned, preferentially aligned NV centers, all aligned in one direction, where dipolar interactions should not average to 0. We can get even higher nitrogen density, which is important, right? We want strong dipolar interactions, so we're able to get up to 50 times higher nitrogen incorporation in this direction. And I'll just skip that slide and summarize and say, I hope that I've convinced you that NV-based imaging yields insight into, I think, already magnetic and electronic properties of condensed matter systems. There's many versatile imaging modalities that we're exploring, and 2D diamond ensembles, NV ensembles, I think will enable higher sensitivity and possible metrological advantages with entangled states. And also interested in looking in hiring postdocs for any of these experiments. So if you're interested, come talk to me. Thank you very much for your attention.
Okay, thanks very much for this beautiful overview. We have time for 1 or 2 short questions.
Thank you for a very interesting talk. Have you considered using your NV spectroscopy for studying superconducting films, especially qubits? Because you showed some cryogenic measurements earlier in the beginning of your talk.
We've definitely thought about that and are interested in. I mean, but do you mean to look at the paramagnetic noise on these qubits, or to look at the superconductivity?
I particularly would be interested in defects between metal and substrate and whatever
Yes,
else
yeah.
you would find.
So short story is yes. I think that would be. I think one of the challenges is our system goes down to 4 Kelvin, and I know that these defects, of course, exist at higher temperatures, but I know that some of these defects are sort of driven, are saturated at higher temperatures, and ideally one would do those experiments, I think, in the operating temperatures of the qubit, down in the millikelvin range, and that's possible, but a bit challenging at very low temperature. But I know Christian Deegan, for instance, has a system that now can do NV sensing at really dilution refrigerator temperatures. But also looking at higher temperatures, I think, could reveal something at what's going on at lower temperatures. So the short story is yes, and happy to discuss more later.
Okay, thank you.
There's one more question in the back.
Thanks for this very beautiful talk. In the end, when you showed measurements of the conductivity, can you also get frequency-resolved optical conductivity this way?
Yeah, so in principle, yes, but I think we are looking at splitting, so our qubit splitting is on the order of gigahertz, which is effectively a DC conductivity, I think, for most systems. So yes, we can tune the splitting of the qubit between approximately 0 or maybe 100 megahertz up to maybe 10, 30 gigahertz in principle. So that's kind of the frequency dependence that we are able to probe.
So you're saying the physics of this NV center limits frequency range that you can access, is that right?
Sort of, yeah, in the fluctuations. I think there are some thoughts on how to access higher frequencies, but not really demonstrated yet. I'd say 30 gigahertz down to approximately DC is currently the realistic working range.
Okay, I think in the interest of time, we should defer further questions to the coffee break. So let's thank Ania again.